Hello developers, welcome to my video series on Microsoft Flight Simulator add-on workflow. Today we're going to learn about PBR and the physics behind it, physically based rendering. We will see how and what PBR is in relation to light energy. I plan to have 3 episodes about the PBR workflow, one on the PBR technical aspects, and then a PBR texture workflow, and then I'll talk about the Microsoft Flight Simulator materials. Now for the physics lesson. Oh, don't turn off the video or skip ahead. It's not that bad. It is, after all, physically based rendering. There are a few good references out there. One is from Algorithmic. It's now part of ADOBE, and their PBR guide part 1 and part 2. Here's part 1, and we'll probably use that. There are no equations to worry about, so I'll reference these documents. This is more of a description of how and why PBR works. Part 1 is about light and a bit technical. Part 2 is about the metallic roughness or PBR workflow, and also about specular glossiness or diffuse workflow. The gist is light from the sun either reflects off a surface or is absorbed and scattered and partially re-emitted. The surface can also be rough or it can be smooth, so reflections are affected by this. Light is made up of energy of different wavelengths, and you've seen a rainbow, so each color in the rainbow represents a particular energy of light. I don't know if you've heard the expression Roigabov, red, orange, yellow, green, blue, violet. We'll be interested in 3 colors, the red, green, and blue, or the RGB colors. You can make up all the other colors based on those 3. There are a number of ways that the values of colors are represented. You could code them as 1, 1, 1, or 255, 255, 255, or in hex, FF, FF, FF. All these code values represent white, or basically all 3 color values, the RGB values, to a max value. So let's look at Blender. Pull up Blender here, and we can highlight an object, go to the materials, we can set a standard material, and we can set up the colors. So the colors are RGB. In this case, we're at 0.8, so 0 to 1 in this particular case, 0 to 8, or 0.8, 0.8, 0.8, and the alpha is 1 in this case. If we look at the hex values, E7, E7, E7. Also, GIMP. So you look at a particular color here. In this particular version, the red is a number based on 0 to 100 or all the way up to 0 to 255. So if we use 255, 255. Produces the color white. So in the PBR guide document, there are 2 texture workflows, the specular glossiness workflow and the metallic roughness workflow. The latter is used in our PBR textures for Microsoft Flight Simulator. The PBR is supposed to provide a more accurate representation of color and textures in a lighted environment. Light rays. The light ray model of light states that light ray has a trajectory of a straight line in a homogeneous transparent medium such as air. The ray model also states that the ray will behave in a predictable manner when encountering surfaces such as opaque objects, or when passing through a different medium such as from air to water. This makes it possible to visualize the path of light ray as it moves from its starting point to another point, where it changes into another form of energy such as heat. A light ray that hits a surface is called the incident ray, and the angle at which it hits is called the angle of incidence. And then as it reflects, it will get a reflected ray with the angle of reflection. The light ray is reflected off the surface. It travels in a different direction. It follows the laws of reflection, which states that the angle of reflection is equal to the angle of incidence. And the light ray that passes into one medium from another in a trajectory or a straight line is refracted. So one is reflected light, one is refracted light. So absorption and scattering. When traveling in a inhomogeneous medium or translucent material, light can be absorbed or scattered. When the light is absorbed, the light intensity decreases as it changes into another form of energy, usually heat. Its color changes as the amount of light absorbed depends on the wavelength, but the direction of the ray doesn't change. When the light is scattered, the ray direction changes randomly, and the amount of the deviation depends on the material. Scattering randomizes the light direction, but does not change its intensity. For example, the person's ear, the ear is thin, the absorption is low, so you can see the scattered light radiating from the back of the ear. It's kind of a picture here, so you get a little bit of scattering. If there's no scattering and the absorption is low, rays can pass directly through the surface. This is the case with glass. For example, imagine you're in a swimming pool, swimming, and it's a nice clean pool. You can open your eyes and see a great distance through the clear water. However, if that same pool is relatively dirty, the dirt particles will scatter the light and lower the clarity of the water, and the distance you can see will be reduced as a result. The further light travels in such a medium, the more it is absorbed and or scattered. Therefore, object thickness plays a large role in how much light is absorbed or scattered. The thickness map can be used to describe objects to the shader as shown in these other views. So for diffuse and specular reflection refers to light that has been reflected at a surface. The light ray is reflected off the surface and travels in a different direction, and we saw that the angle of incidence equals the angle of reflection. But however, most surfaces are regular and the reflected direction will vary randomly based on the surface roughness. And this changes the light direction, but the light intensity remains constant. Rougher surfaces will have highlights that are large and appear dimmer, so a rough surface here. Smoother surfaces will keep the specular reflections focused, and they will appear to look brighter and more intense when viewed at the proper angle. So here we have a specular reflection. However, the same total amount of light is reflected in both cases. So you have to understand that the amount of light here is the same as the amount of light here, or the energy is the same. So here we have some diagrams where we have a smooth surface, the incident ray and the specular reflection is focused, like in the previous picture, and here we have the incident ray where everything is refracted, and the diffuse direction, all sorts of different directions for the light, which is this example here. Refraction is the change of the light's direction. So when light moves from one medium to another, it changes its speed and direction. The index of refraction, or IOR, is an optical measurement that describes the change in the light ray is traveling. Essentially, the IOR value is used to determine how much the ray will be bent when it passes through one medium to another. So for example, you see a glass of water here. You notice that the straw and the light that you see from the refracted glass and the water and glass is all different. So the light is being refracted or changing direction, and when it changes direction, it appears to come from a different point than you would expect. So a diffuse reflection is the light that has been refracted. The ray may pass from one medium to another, or in our example, we'll assume that it enters an object. The light is then scattered multiple times within the object. It is then finally refracted again out of the object, making its way back to the original medium at approximately the same point where it initially entered. Diffuse materials are absorbent. If the refracted light travels for too long in such a material, it may be absorbed completely, and if the light does exit this material, it has likely traveled only a very small distance from the point of entry. In this diagram here, we took one of the previous diagrams and we've blown it up a little bit, and we'll show you one incident ray that can have a specular reflection here in orange, or the incident ray can be absorbed and it hits other scattering particles and gets refracted and bounced around until a point where it gets re-emitted out of the surface of this particular object. So we have an incident ray with specular reflection, and we have an incident ray with diffuse reflection. So in microfacet theory, basically the surface is not a flat surface, perfectly flat surface. What you have is you have microscopic bumps on the surface. So these microscopic bumps now, where the incident ray comes in, the reflection or reflected ray off of that surface goes all over the place. So the microsurface, you've got a normal, which is the blue, incident ray, reflected ray, etc. Two common ways that you get a reduced amount of light or reflected energy is shadowing, where the incoming ray can't hit a part of the surface, or the reflected ray ends up being blocked by another part of the surface. So basically, what it says here is the theory both diffuse and specular reflection are dependent on the surface irregularities where light rays intersect with the medium. In practice, however, the effect of roughness on the diffuse reflection is less visible because the scattering that occurs inside the material and not based on reflection itself. As to color or visible color of a surface is due to the wavelengths that are emitted by the light source. So the sun emits a white light, or all the colors of the rainbow. These wavelengths are then absorbed by the object and reflected both specularly and diffusely. The remaining reflected wavelengths are what we see as color. So the incoming white light here, so all the different colors of the rainbow, red, orange, yellow, green, blue, violet. We see that orange, yellow, green, blue, and violet are all absorbed by the apple. The only part of the light energy that gets reflected is the red, and that's why we see an apple with the color red. So there is a thing called a BRDF, which is a bidirectional reflectance distribution function. Okay, a little bit of math. Not going to go into it, but basically the computers use this type of function to generate the graphics. What we have also is energy conservation. Energy conservation plays a vital role in the physically based rendering solutions. The principle states that the total amount of light re-emitted by a surface, reflected and scattered back, is less than the total amount received in. In other words, the light reflected from the surface will never be more intense than it was before it hit the surface. So yeah, we're just going to understand that in some cases you could make shaders where you can have more light being emitted from the surface that actually was transmitted to it. So the Fresnel effect, it's not something that we control in PBR as we did in traditional shading. So previous things like FSX may have allowed you to input the Fresnel effect as part of the texture. It's another aspect of the physics that's handled by the PBR shader. When viewing a surface at grazing instance, all the smooth surfaces will become reflectors at nearly 100%. So at 90-degree angle of incidence, you basically see a reflection. This can be looked at as you're looking at a pool, for instance. If you look straight down into the pool, you can see the bottom of the pool. But if you step back from the pool and you start looking at it at an angle, you can start to see reflections at the surface of the water. This is the Fresnel effect. The Fresnel reflectance at 0 degrees is called F0. So when light hits the surface straight on in a perpendicular manner or 0-degree angle, the percentage of that light that is reflected as specular. Using the index of refraction for the surface, you can derive the amount that is reflected. This is referred to as the Fresnel zero. The amount of light that is refracted into the surface is referred to as 1 minus F0. So the F0 range for most common dielectrics. So a dielectric is opposite from metallic. So metals conduct electricity, a dielectric does not conduct electricity. So that's how they refer to that. So the F0 range for most common dielectrics is 0.02 to 0.05 or 2 to 5%. So the light that gets reflected is 2 to 5%. For conductors, or metallic things, the F0 range will be 0.5 to 1. So it'll be 50% reflective at the F0 angle, or even 100% reflective. So that's kind of the difference between something being metallic and something being non-metallic. And this is where we're going to start to get into the metallic roughness workflow in PBR. Oh my God, my eyes. Well, that's an equation. So basically n is the index of refraction, so the F0 is calculated by n minus 1 squared divided by n plus 1 squared, and that's how they got the 0.02. So now we'll start to pull some things together here, talking about the roughness metallic workflows and so forth. So conductors and insulators, metals and non-metals. So when creating materials for PBR, it's helpful to think in terms of metal or non-metal, and you ask yourself if the surface is metal or not, basically yes or no. If it is, you will need to follow one set of guidelines, and if it's not, you need to follow another. And this can be a simplistic approach, as some materials may not fall into these categories, and I don't think we have to deal with those in Flight Simulator. But the overall process of creating materials is distinguishing them between metal and non-metal. A good approach is to set up some guidelines for the materials. We first have to understand what we're trying to create. And with PBR, we can look at the properties of metals or conductors and non-metals, insulators, to derive this set of guidelines and shown here. So plastic, rusted metal, water, ice, glass, they have RGB values of 55, 64, somewhere around the 50, 60 or less range. While gold will have an RGB value or color value of something higher, something above 230. Iron down to 190s, something like that for these RGB values. An important aspect to understand is that refracted light is absorbed and the color tint of the metals comes from the reflected light. So in our maps, we don't give metals a diffuse color. So we'll talk about diffuse maps and so forth a little later, but just understand that you don't get the color of a metal from refracted light, you get it from the reflected light. So metals are a good conductor of heat and electricity. The electric field in conducting metals is zero, and when the incoming light wave made of electric and magnetic fields hits the surface, the wave is partially reflected and all the refracted light is absorbed. The reflectance value for the polished metal is at a high range in the 70 to 100% area that's reflective. So the incident ray comes in, anything that enters into the surface of the metal is completely absorbed. There's nothing being refracted and scattered and re-emitted. Everything here is a reflective ray that you see in a metal. For nonmetals or insulators or dielectrics are poor conductors of electricity. The refracted light is scattered and or absorbed, often re-emerging from the surface. So they reflect a much smaller amount of light than metals do and will have an albedo color. So there'll be a color based on that refracted light that gets re-emitted. So common dielectrics have a 2 to 5% F0. So this diagram here is kind of showing you that from 2 to 5%, with the 4% being a common number that is kind of built into the PBR workflow. So this is what we'll talk about when we get things down to 4%. That would be somewhere around 59 sRGB or standard RGB. There's another thing here that's a linear space rendering. It's a highly complex subject. For this guide, we take a simplistic approach in stating that the linear space rendering provides the correct math for the lighting calculations. So all of this is all internal. They talk about gammas and stuff like that. I don't want to get bogged down into this. You can read this section. Close your eyes. There's more equations. So linear color is the color in sRGB to the power 2.2. That's where the gamma comes in. Now the online documentation talks about key characteristics and then doesn't mention them. It just goes into some of the footnotes. But if you download the PDF will tell you the key characteristics of PBR. So we're going to sum everything up based on these statements. So energy conservation, a reflected ray is never brighter than the value it had when it first struck the surface. Energy conservation is handled by the shaders. There's the Fresnel part, so the BRDF is handled by the shader. You may see in Blender we have a BSDF, so that's the shader that is used in the blender. The F0 reflectance value has a minimal change for most common dielectrics and falls within the 2 to 5%, and the F0 for metals has a high range, 70 to 100%. Specular intensity is controlled through the BRDF, roughness or glossiness maps, and then the F0 reflectance value. We talk about roughness and glossiness. There's a roughness metallic workflow and the glossiness specular workflow or diffuse. They can both be used in PBR, but the roughness metallic one is better, and we'll describe that in the next section. Lighting calculations are computed in linear space, so none of that gamma stuff. All the maps have been gamma encoded. Values such as base color or diffuse are usually converted by the shader to linear. But you may have to ensure that the conversion is properly handled by checking the appropriate option when importing the image into your game engine or render. So those types of things we might be able to adjust with some of the Microsoft Flight Simulator material parameters. So the maps that describe the surface attributes such as roughness, glossiness, metallic, and height should be set to be interpreted as linear. And I think that Substance Painter kind of takes care of this. So the physics lesson is over and you come out now. So in the next part, we'll apply what we've learned here to the PBR workflows, namely the metallic roughness or the specular glossiness concepts, and we'll deal with that in our next episode. So good luck and see you next time.